Today we are going to study the last part of chapter 5, and we are going to discuss the wave phenomena, the intensity of the waves, and Doppler effect. And let's start with the wave phenomena. These phenomena occur in any type of waves, and the phenomena are refraction, reflection, diffraction, interference, and resonance. And all of these phenomena occur when the wave interacts with the surrounding environment. Let's start with refraction and reflection. Then, what happens when the wave that is traveling change from one medium to another medium? Then, because the velocity of the wave depends on the medium, then the velocity of the wave change. And this is why the direction of the wave when passed from one medium to another medium also change. And what occurs is the wave bend. Yes, occurs some bending of the wave, we can see here. And this is why we can say the refraction is the bending of a wave. And maybe it will be easier to remember the refraction is associated with the bending of a wave. And one example we can see clearly is when the light passes from air. Yes, here we had the light is traveling in air. Then now the light is traveling in water. And what happened? The velocity of the light is changes, and this is why we can see this phenomenon. And this corresponds to the refraction phenomenon. In other case which refraction can occur is when the conditions of the medium change. For example, if the sound is traveling in air and the temperature of the air changed, even if we had if the sound is traveling in the same medium, but if the condition changed, then also the refraction occurs. Yes, because the velocity of the wave change. Then there will be occur some bending in a wave. The other phenomenon is the reflection. The reflection occurs when the wave hits an object and the wave bounces off. Yes, then this happens when the wave hits an object and then the wave bounces off. Then we can associate reflection with the word bounces off. Yes, it will be easier to remember the concept of reflection. And here we had one example is when the light hit the mirror, the surface of the mirror, and then bounces off. But also refraction occurs in sound. Yes, in sounds. The previous example we had for light, but here is for sound. Then refraction of sound can explain this question: why can you hear sound better at night? And the answer is because of the refraction of sound. And what happens is during the day, because of the sun, the surface, the ground is hot. Then the air close to the surface is warm, but the air in the upper part is cold. Then because we know this, the velocity of the sound depends on the temperature. Then because of different temperature, the sound in the way of the sound refract, and this is why there is some bending in a wave in this direction. But what happened during the night is the opposite situation. Because there is no sun, then the surface will be cold, and then the air will be cold. And what happens is the air in the upper part will be warm. And in this case, the bending in the wave will be occur in opposite direction, as in this direction. And this is why we can hear sound better at night. Also, the reflection occurs in case of the sound. Then what happens is when the sound wave traveling through the air, for example, it can travel through the air and hit some surface, then the sound will be bounces off, yes, will be reflected. And this is why we can hear like the sound is repeating. Yes. If the reflected sound is the echo arrive after 0.10 seconds, the human can distinguish the reflection sound from the original sound. And we know this phenomenon is called echo. And this phenomenon is used by some of the animals, for example, to harm the prey. Yes, and this is called the echolocation. Yes, they use that phenomenon to know what is the position of the prey. Let's try now to solve one problem that involves the sound wave. Then in this case, the problem says the human ear can distinguish a reflected sound pulse from the original sound pulse if 0.10 or more elapses. If the difference between the original sound and the echo is 0.10 seconds, then we can distinguish two sounds. The question is, what is the minimum distance to a reflecting surface from which we can hear an echo if the speed of the sound is 343 meters per second. Then here is where is the source of sound, and this the sound wave we will travel, and then will be hit some surface here. Yes, here we will have some obstacle, and because of this obstacle, then the sound will be reflected, will be bounces off. Yes, we will travel. Then from this point, when the sounds travel from the surface, hit the obstacle, and then back to the surface, the time is let me try to down. The time is 0.10 seconds. And we know the velocity of the sound is 343 meters per second. Then we want to know what is this distance, is the minimum distance. Let me, the minimum distance. What is the minimum distance in which we can distinguish the echo from the original sound? Then here we want to calculate the minimum distance. And what happens, because the velocity is constant, then we can apply this equation. As this is the equation we can use to describe any motion at constant velocity. This is why we don't have here the average velocity because the velocity is constant. Then let's calculate the distance first, and then we will try to analyze the answer. If this is the answer, we need to do something else. And we want to solve for the time. Then we have distance equals to the divided by the time. And distance equals to the velocity is 343 meters per second multiplied by the time, 10 seconds. Here we have 34.3, and let's see the units. This cancel out with this one, then we have meters. Then the question is this the minimum distance? This is the distance we are trying to find? Then the answer is no, because this time corresponds to the distance when the sound is traveling in this direction and then when the sound bounces off. Then we don't want all this distance, we just want from this point to this point. Then what we want to calculate is half of this distance. And here we had to be careful with the significant digits. We had two significant digits here, then this should be 34 meters. Then we had in this case is twice of the distance we want. Yes, we want just the distance from this point to this point. Then to calculate the distance, the minimum distance, what we need to do, we need to divide this one by 2. It's 34 meters divided by 2, and this minimum distance will be 17 meters. And this corresponds to about 56 feet. And I know you understand, you know better feet. This is, you had idea how far, what is the minimum distance in order to distinguish the original sound from the echo. This is one way you can solve the problem. The other way you can solve the problem is you can divide the time by 2 and then calculate the distance. Then you will calculate from this point to this point from half of this time, and you will get the same answer. You will get 17 meters. Then you can solve in either way. And up to now we have studied two phenomena. One is the refraction, and this occurs when the wave bends, and the other is the reflection. The reflection occurs when the wave bounces off. Then now we are going to study another phenomenon, which is diffraction. And just suppose you go a concert and you got a seat in front of the large post, right here. But still you will able to hear the concert quite well. And the reason is you can hear the concert is because the sounds can travel around the edges of the obstacles. But if you were outside, still you can hear the sound, because the sound can pass through a small opening, like in this case, can pass through a small opening. It were a new source of sound localized in this point. And here we have one more example. Yes, if a student is in the corridor, then she can hear the radio, the music, because the sounds can travel around the edges of the corridor. Then the diffraction, we can associate the diffraction that the sound or the wave, it can travel around the edges of the obstacles. Another phenomenon associated with the waves is the interference, and this occurs when two traveling waves meet. Then they can interfere with each other, producing a new disturbance. In other words, producing a new wave. And what happens if two in-phase waves they interact? Then we will have a new wave with crest and throw reinforced. And we will have a new wave with the double of the amplitude. And these two amplitudes will be reinforced, and we will have a new wave with the double of the amplitude. Now, if two waves out of phase interact, then what happens is the crest and throw will be cancelled. And we don't have wave, as in that case. They will cancel each other. But after the wave pass through to one another and return and then the wave will be returned to the original amplitude. And after this one pass one other, then the waves will be returned to the original amplitude. Then one of the phenomena in which the interference is applied is in the case of the standing waves. One example of the standing waves is the strings in a guitar. And in this case, the ends of the string are fixed. And now what happens when we apply a force to the string of a guitar? Then what happens is the incoming wave, yes, the string in a guitar is vibrating. Then the incoming wave will be interact with the reflected wave. Then the interaction between the incoming wave and the reflected wave will be create a pattern of node and antinodes. Then the nodes correspond where there is destructive interference, and the antinodes correspond where the interference is constructive. Then the pattern of the nodes and antinodes depend on the tension of the string, depend on the frequency of the vibration, depend on if the string is thick or is thin. Then there are many variables that is needed to take into account if to create patterns of node and antinode. And in the next video, we are going to see how the standing waves are generated. And let me show the video and you can see that. Here we can see the different patterns for node and antinode that depend on the frequency of the vibration that travels through the string. Then if we had one antinode, this is called the fundamental frequency. If we had more than one antinode, then this is called overtone frequencies. And when the people make music, they combine the fundamental frequencies with the overtone, and then they can get a characteristic sound, and sounds like music sound. The other phenomenon associated with the waves is the resonance. Probably you had seen this in a movie when a singer shatters a crystal water glass by singing a single note, but the other objects remain undisturbed. And why this happens? Then we already know all the elastic materials can vibrate. But all the elastic objects, they had a natural frequency of vibration that is determined by the material and the shape of the object. When any external frequency matches with the natural frequency of the object, this phenomenon is called the resonance. And the natural frequency of the object is called the resonant frequency. And why this breaks? The reason is if the external frequency matches with the resonant frequency of the material, then the energy is transmitted efficiently. And this is why the molecules, or we can say the molecules of the crystal start vibrate faster. And this is why in one point the crystal is going to break. I would like to show a video in which you will see what happens when the external form matches with the natural frequency of an object. And we already say if that happens, the energy will be travel through the object efficiently, and then the molecules start vibrating faster and faster and faster. Then that energy will increase the kinetic energy of the molecules, and the molecules start moving faster and faster, and in one point the object can be a crystal will be break. And let's see the video. Another example of the resonance occurs when the natural frequency of two four-stroke matches. And what happens if you stroke one tuning fork, but you don't stroke the second one? But because the natural frequency of these two matches, then the energy is going to transfer efficiently. Then the second one start vibrating. Then let's see the demonstration in the next video. In this case, they modify the natural frequency of one of the stroke, and this is why now the second one doesn't vibrate. Now let's talk about the intensity of the sound. Then before define what is intensity, let's review the concept of power. Then power is how much work can be done in unit time. But we know when we work on some system, we are giving energy to that system. And this is why we can define also the power as the rate of energy. It's how much energy per unit time. Also, we study the units of powers are watts, because it's units of energy or work, which is joule per second, which is defined as watt. And now let's define intensity. Then the intensity is how much rate of energy can transfer by the wave in some area if the waves are perpendicular to that area. Then the intensity is what is the rate of energy that is transferred by the wave to some area if the wave is perpendicular to that area. Then this is why we can define intensity as power, because power we know is the rate of energy. Yes, is the rate of energy. Power is the rate of energy. Then the intensity is the rate of energy. And we can write here intensity equals to the rate of energy per area. But we know the rate of energy, this is energy over time, equals to power. This is why we can define the intensity as power over area. Then let's check what are the units for intensity. The units for power is watts, and the units for area in the SI system is meter square. This is why one of the units for intensity, in this case we are talking about the intensity of sound, is watts per meter square. One more thing is, if we analyze this equation, we can see the intensity and the area, they are inversely proportional. More area, less intensity. Yes, because if we analyze this equation, if we apply the line test, they are in opposite. One is on top, the other is on bottom. Then larger area, less intensity. And this is why if here we had some source of sound or light, yes, what happened if we move far from the source of sound, then the area covered is larger, and this is why the intensity of the sound decreases if we move far from the source of the sound. Then we already discussed there is some range in frequency we can hear, and this range is between 20 Hz and 20,000 Hz. Let's now talk about the intensity. And in this scale, the units of the intensity is watts per meter square. We already discussed is the rate of energy per area. Yes, per area. Then what we can see is in this scale we had some power of 10, we had some negative exponents. And there's another alternative units for sound intensity, which is decibel. And in this scale, decibel is based on the order of magnitude. you can see from here we had 12 order of magnitude, and this is here we had the scale from 0 to 120. In this scale, let's see what are the intensity of the sounds we can tolerate. Then from 0 to about 30 decibel that corresponds to quiet sound. From 30 to 50 decibel, this corresponds to the normal sound, like my voice right now. Then for 50 to 80 decibel, this corresponds to loud sound. But about 80 decibels is start with discomfort, is danger. But about 110, 120 is really harmful. It's really, you can feel pain if you hear that the sound at this intensity. The intensity is related to the loudness of the sound, and the loudness of the sound is related to the amplitude. Then larger amplitude of the sound wave correspond to louder sound. Then more amplitude in the sound wave correspond to larger intensity, louder sound, and small amplitude correspond to the quiet sound or less intensity. In this graph, we had two different sound waves. In the second one, we had greater amplitude and higher frequency. But in the second one, we had lesser amplitude and lesser frequency. And how we can associate this with the sound we can hear. And if this wave has greater amplitude, then will we have greater loudness, and also will we have greater intensity. If this has higher frequency, then we will have greater pitch. In the other case, in which we have lesser amplitude, we have lesser loudness and lesser intensity. And we have lesser frequency and lesser pitch. And now we know the higher frequency corresponds to high pitch and low frequency corresponds to low pitch. And also pitch. When we had higher frequency, we had a small wavelength, yes? And if we had a small frequency, then we had larger wavelength. And in this case, we are comparing the frequency sound for two different instruments, and what happened is, because the amplitude is the same for both waves, then we know the intensity is the same. However, the pitch is different. In the pitch sound is different. In the first one, we had lower pitch sound because we had lower frequency. But in the second one, we had high pitch sound with higher frequency. Now we are going to study the Doppler effect, and this occurs when a moving source of sound or a moving observer experiences an apparent shift of frequency. And let's see what happened in the last image we had here. Then in this case, this is the source of sound. Here the source of sound, and here we had the observer. Then the observer and the source of sound are not moving. And we can see there is no change in the wavelength, and there is no change in frequency, or the apparent change in frequency. Now, what happens if the source of sound is moving to the right? Then the observer is here will be perceived the wavelength is decreases. As we can see here, this is correspond to the wavelength, as that part correspond to the wavelength decreases. And we know if the wavelength decreases, then the frequency is going to increase. Then this observer will be perceive higher frequency. There is change in frequency, higher the sounds at higher frequency. But the observer on the other side will be perceive that the wavelength is increases, as is larger. In this case, we can see here this corresponds to the wavelength. And then that observer will be perceive the frequency decreases. And this is why here, when we define the Doppler effect, there is the apparent shift of frequency. In this animation, we will see how when the source of sound is moving respect to the observer, the wavelength change. And when the B, which is the source of sound, is approaching to, we can think this is the observer. When it's approaching to the observer, the wavelength will be decreased. As we can see now how the wavelength is decreases, and this is why this, if this is the observer, will be perceived the frequency increases. But if the B is moving far from the observer, what is happening is we will see there is increasing in the wavelength that is happening now, the increases in the wavelength, and then will be decreases in the frequency. And this is why the Doppler effect is related the shift in frequency when the either the observer or the source of sound is moving. Let's review what is the Doppler effect. The Doppler effect is the apparent change of wavelength and frequency of the wave when the source is moving relative to an observer. And in this picture, we can see if the source of the sound and the observers are at rest, they are not moving, then there is no change in the wavelength, and if there is no change in the wavelength, there is no change in frequency. Then in the other figure, what we can see, if the source of the sound is moving towards the observer, then there is the apparent change in the wavelength decreases, and then this is why the frequency increases. And in the other side, we can see the wavelength increases, and this is the frequency decreases. And this is how we can summarize the Doppler effect in case of the sound wave. And this is all I had to discuss for today.